Have you ever really wondered what's going on inside the mind of a machine when it's learning? We hear about AI all the time, but how does a computer actually go from looking at a bunch of raw data to making a smart, useful prediction? Well, today, we're going to pull back the curtain and demystify that whole process step by step. So let's just jump right in with a really important question. Is it possible for a computer to look at a patient's age, their cholesterol levels, their blood pressure, and actually make an accurate prediction about their risk of heart disease? This is exactly the kind of problem that machine learning was designed to tackle.
So, how does that even work? How do we get from a simple number, like someone's cholesterol, all the way to a prediction that could potentially save a life? Well, that's the whole journey we're talking about, from data to decisions. At its heart, machine learning is all about teaching a computer to find the hidden patterns in that data, the subtle connections that a human might not spot.
Now, the specific method we're going to focus on is called supervised learning. And honestly, the best way to think about it is like teaching a toddler with flashcards. You show them a picture of a cat, you say cat. You show them a dog, you say dog. You do that enough times, and pretty soon they can tell the difference on their own. We're doing the exact same thing, just with data instead of fluffy animals. Okay, so every investigation needs clues, right? And for our digital detective, the AI model, those clues are the data. The quality of this data, well, it's pretty much everything. So let's crack open a few of the case files our model is going to be working with. First up are heart disease data. Each one of these rows is a different patient with their vital stats. Now, the most important part is that last column, heart disease. See the ones and zeros? A 1 means yes, they have it, and a 0 means no. This is the correct answer on our flashcard. This is what the machine is going to learn from. Our second case, this one's a total classic in the machine learning world. Here, the clues are the measurements of a flower's petals and sepals, and the goal? To correctly figure out which of the 3 species of iris flower it is. It's a classification problem. And for our final case file, something a little tastier, breakfast cereals. We've got all the nutritional info like calories, sugar, and protein, and it's all paired with a consumer rating. The machine's job here is to figure out what combination of nutritional facts leads to a really high rating. Okay, so we've got our clues, we've got our data. Now it is time for the study session. This is the part where we hand over all this information to our machine and basically say, okay, figure out the relationships between these clues and the final answer. But wait a second. This brings up a huge problem, right? If we give our model all the data to study, how can we be sure it actually learned the patterns and didn't just, memorize the answers? You can't give a student a final exam with the exact same questions they had for homework. That's cheating. And the solution is actually pretty simple, but it's totally brilliant. It's called the train-test split. We give the machine the majority of the data, say 70% of it, and that's its study material. But we keep the other 30% hidden away. That becomes the final exam. The machine never, ever gets to see the test questions ahead of time. And you know what's wild? The actual learning part, it all kicks off with a single command, just like this one. It's basically like telling the student, all right, here are the books, go study. And at that point, the machine just goes to work, churning through all that training data to find those hidden patterns we've been talking about. Okay, the study session is officially over. It is now time for the final exam. We're about to take that 30% of data that our model has never seen before, and we're going to ask it to make predictions. This is the moment of truth. Let's see how well it really learned. And here it is, the first report card for our heart disease model. Okay, let's break this down. Precision is about being careful. When our model says a patient has heart disease, how often is it right? We don't want false alarms. Recall, on the other hand, is about being thorough. Of all the people who actually have heart disease, how many did our model find? We don't want to miss anyone. It's a real balancing act. So what's the overall grade? On its very first try, our model got an accuracy of 65%. Okay, not amazing, but it's a start. It's definitely better than just flipping a coin. But the real question is, can we do better? Of course we can. This is where we become the model's personal tutor. It's a process called hyperparameter tuning. Think of it like trying to find the perfect study technique for a student. Should they study for 1 hour or 3? Should they use flashcards or just read the textbook? We systematically try out all these different settings to find the one combination that helps our model learn the most effectively. So after all that extra tutoring, we test it again. And wait, what's this? The score actually went down a little bit. Now, this is a fantastic example of a really key idea in machine learning. Sometimes, if you try to make a model too perfect for one specific test, you can actually make it less flexible and worse on other tests. The goal isn't just to ace one exam, it's to build a model that's reliable and robust out in the real world. So we've seen how to train and test a single model. But that leads to another question. What if we were just using the wrong type of model to begin with? For some problems, a hammer is the right tool. For others, you really need a screwdriver. So let's find out which tool is the best for our serial data. So we set up a competition, a little showdown between 3 different kinds of expert models. We trained all of them on the exact same serial data, and their report cards are pretty fascinating. Look at this. One model, the random forest, had perfect recall. It found every single high-rated serial. Another one, the perceptron, had perfect precision. Every serial it said was high-rated actually was. They have different strengths. But if we're just looking at the overall grade, the final accuracy, well, there is a clear winner. The random forest model got it right almost 94% of the time. For this specific job, it was, without a doubt, the best tool. And that right there, that's the real secret. There is no magic, one-size-fits-all model in AI. Whether you're trying to predict heart disease or just figure out which serial is going to be a hit, the process is always about testing a few different experts and letting the data tell you which one is the right tool for that specific job. So, there you have it. We've pulled back the curtain and seen how machines go from just a pile of raw data to making intelligent predictions. It's about gathering clues, taking a fair test, and always finding the right expert for the job. It's an incredibly powerful process that is already changing our world, which leaves us with the biggest, most exciting question of all.